Hi everyone. Okay, this is the introduction to the projective plane. In order to move on with our um, study of elliptic curves, we need to understand the projective planes. So I'm making this series of videos to sort of introduce us to the projective plane and homogeneous coordinates. In order to do that, we need to know a little bit of vector operations and vector manipulation. And so I just thought I would take the time. So frequently, it's so hard to find a good explanation of the dot product and the determinant and the cross product. So I'm going to take the time to present those in a way that I understand them, that helps me really understand them instead of just knowing the rote equations or the formula for each one. So this video is the dot product, and then we'll go on to the determinant, and then I'm going to justify the cross product, which is something you almost never see, and then quickly equation of the plane, and then we'll get to the actual projective plane and homogeneous coordinates. So here we go with dot product.
Okay, dot product. I want to just try to explain how to think about the dot product in what I hope is an intuitive way. Because the way that it's usually explained is that if you have two vectors, that the dot product is the projection of B onto A, and then you multiply the two magnitudes that way. But first of all, it doesn't really make sense to me, and it's a weird two operation. You're projecting and then multiplying. They say that the dot product's a projection, but it's not really a projection. This is the projection, and then you're also multiplying. It's a projection if it's just times the unit vector, but we'll get to that. So the definition, the other standard algebraic definition, is that if you have two vectors and B we all learned this in school, that A dot B is A1 B1 plus A2 B2 plus A3 B3. And that really is what the dot product is. I think the way to think about it is we're talking about how to multiply two vectors together. There's two ways that we can, or there's a few ways we can do it. But one way is to ask how much are the components scaling in each direction, in the same direction. And then the other way, which is what the determinant and the cross product are, is how are they affecting each other in the other direction. So like how much does the component of one affect the other components on the other vector? So the dot product is comparing the same components on each one. So if we have two vectors, we multiply how much are they going together this way, how much are they going, and add that to how much are they going together this way. The important point is that we don't end up with a vector. That's the other reason that I think this is a strange way of looking at it, because we're not projecting B onto A and then multiplying. That kind of implies you end up with a longer vector in the direction of A. That's not accurate. What we end up with is a scalar. It's just a number. What it is just it's just the sort of a multiplication of the magnitudes of the vectors in the different directions. If we're looking in one direction, if we're looking in one dimension, just a real number line, something like this, and we have maybe 2 and maybe 3, and we multiply these together, we take 3, scale it, double it, and we end up with 6, right? So that's how multiplication works in one direction. So multiplication with vectors, if we're multiplying the magnitude, it works the same way, especially if the two vectors are in the same direction, and we want to multiply these two. This is A, this is B. Say this has a length of 2, this has a length of 3. Then we do the same thing. We take say we take the 2, scale it by a factor of 3, and we end up with a vector that has we end up with a magnitude of 6. But again, this is why it gets confusing, because the point is that the 6 is not a vector in this direction, it's just the magnitudes. In one dimension, it's just the magnitudes. In 2 dimensions or more dimensions, it's also just the magnitude. So if the vectors are in the same direction, then it looks exactly like real number line multiplication. But what the question is, but if we're multiplying 2 vectors that are not in the same direction, what are we actually doing? If they were in the same direction, then this magnitude would scale this magnitude the full way. If this was 3 and this was 2, it would scale it, it would double it. But if it's not going in quite the same direction, then it's not going to scale it fully. You're going to end up with something less than that. And that's why, so what we're doing is, if you had 2 vectors, say this is, say 2, 1, and this is 1, 2. So we're looking at how much do they scale each other in one direction, plus how much do they scale each other in the other direction. So it would be 1 times 2 plus 2 times 1, and that would be 4. So, yeah, so interestingly, in this case, it would actually be the same as if they multiplied them. Oh, no, because the distance is different. Okay, so if we look at, let's just look at one example. If we look at another example where I just wanted to show you that this works even if they're in the same direction. If we have one vector that's 1 by 2 and another vector that's 2 by 4, and we multiply those, if we just take the dot product of them, so this is 2 comma 1, this is 4 comma 2. If we take the dot product, we end up with A dot B equals 2 times 4 plus 1 times 2, which gives us 10. That's the magnitude if you multiply these, because they're in the same direction. What if we actually multiplied the magnitudes, what do we come up with? So what's the length of this? Just use the Pythagorean theorem. So the distance of the length of A is 2 squared plus 1 squared, and then we take the square root of that. So 4, 5 equals square root of 5, right? For B, we have the square root of 4 plus the square root of 2. I'm sorry, 4 squared plus 2 squared, square root of the whole thing, that's 16, and 4 is 20. So the square root of that. That's the length of A and the length of B. So if we multiply those two together, square root of 5 times the square root of 20 is the square root of 100, which equals 10. So it works when they're multiplying in the same direction. So if they're not quite in the same direction, then they're pulling each other in sort of, there's more tension, and they end up not scaling to the same degree that they did before. And then, of course, if they're pointing in completely opposite directions, orthogonally, then they're not going to do anything to each other, because this one doesn't scale this one at all. The scale along this direction is 0, and the scale along this direction is 0. So if A is perpendicular to B, then A dot B is 0, right? So if you take the dot product, and the dot product is 0 whenever they're orthogonal. So what I want to look at, though, is now, but as I said before, there is another definition of the dot product. The way it's commonly given is with this formula. Where if we have two vectors with an angle theta between them, this says that we're taking the length of A times the length of B times the cosine of theta, which basically projects this down, and then we're multiplying this. So we're sort of multiplying the length of A along, or the length of B along A times A to get A dot B. But I want to show us, I want to demonstrate why that's true. So first of all, again, if we look at two vectors that are in the same direction, it's obviously true because then the cosine of this, the angle is 0. So the cosine of 0 equals 1. So in this case, if they're in the same direction, you're just going to multiply the length of one times the length of the other, right? So that matches. And cosine of 90 degrees, or pi over 2, is 0. So again, if they're orthogonal, then this is going to be 0. So this will all be 0, which is what we got before. But that doesn't really explain. It looks like we're projecting one onto the other. So I just wanted to show you how the algebraic definition of dot product will lead you to this, which is useful. But I think it's a little bit misleading because we're not really projecting B onto A and multiplying, but you can look at it in this way. So okay, so first, if we have a vector A, and just A1, A2, dot, 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 AN. Then we can define, let's say let's say that I just have one that's in 2 dimensions. A goes out here. We want to know the X component and the Y component. So if we have an angle theta here, the definition of cosine is the adjacent over the hypotenuse. We all learned that as well. So it's this distance over the length of A, right? So then if we multiply the hypotenuse over to the other side, we end up with adjacent equals hypotenuse times cosine. So if what we want is the component of A along the x-axis, then we can call this E1, this E2. We can see that if this is the vector, then the component that's along the x-axis is exactly, so say the first element here is the length of A times the cosine of theta times the cosine of this theta. Okay, that's what we just had here. So then the length, this is A1, and then A2 is the same thing with a different angle. So A2 equals the length of A times the cosine of theta 2. Okay, so that's the first step. And then the distance formula, just to remind you, the distance formula is always, if you have any two-dimensional thing in 2D space, it's just the Pythagorean theorem, right? It's the distance along x squared plus the distance along y squared equals the hypotenuse squared. So again, if this is A, then the length of A squared equals the length along x plus the length along y. And then this is all squared. If we took the square root of this, take the square root of that, and you would have the length of A. And a couple more pieces of information. So the definition, I just want to write it down again in summation form. A dot B is all of the A's times all of the B's, the summation of those. So if we have A equals A1, comma, and B equals B1, this just says that it's A1 times A1 plus A1 or A2 times A2, A3 times A3, and so on up to AN. That's what the dot product equals. Finally, we need the law of cosines, which is c squared equals a squared plus b squared minus 2ab cosine of some angle, of the angle between the two. That means if we have an angle here and the sides A, B, C, then the length of this side, C squared, equals this squared plus this squared minus 2 times these times the cosine of C. So you can derive this too. I'm not going to bother with that now, but if you want me to, ask in the comments and I'll be happy to. So we're going to use this to derive the alternate. What we want is that A times B, or A dot product B, is A, B, cosine of the angle between them. So if we have, just draw it a little bigger. We have two vectors. This is A and this is B. So this vector from here to here is A minus B. So this is A minus B. So A minus B equals, it's A1 minus B1, A2 minus B2, AN minus BN, right? That's just this vector. So now we're going to plug this, we're going to plug all of our vectors into this, the law of cosines to give us, well, we're going to end up here, but so let's just plug it in and see what we get. So if we have the length of this one squared, so the length of A minus B squared equals oh, I'm sorry, wait, I missed a step first. First, I want to tell you, first we know we can figure out the length of this one using the distance formula, which was this one, was this here. So you just square each component and take the square root of the whole thing and add them together. That's how you get the distance. So the first thing I need is that the length of A minus B is A1 minus B1 squared plus A2 minus B2 squared plus AN minus BN squared. Okay, this is just the Pythagorean theorem. That's the length of A minus B. And then the length of A is A1 squared plus A2 squared plus. We can rewrite that in the summation as AI squared. And I should have written, we can write this one as AI minus BI squared. And then B, of course, is the same thing. Equals BI squared. Okay, now plugging these equations into the law of cosines up here, what we're trying to do, we're plugging them into this triangle. And we have an angle here. So the left side is the a minus b. So we want the length of a minus b squared. That's this one. So I'm just going to plug it in. I'm going to plug in this. Well, I'll write it down first. So a minus b squared equals, and then a squared, the length of a squared, plus the length of b squared, minus 2ab cosine c, minus 2a b cosine c. Now, if we expand this out, we end up with the sum of, so the left side, oh, so I just wanted to rewrite this as, actually I need more room. Let me go to another page, okay? Okay, so I'm rewriting these using the summation formula. Just it's a little easier to write to work with. So we have that the sum of ai minus bi squared, that's the length of a minus b squared, equals the sum of ai squared, that's the length of a squared, plus the sum of bi squared minus 2 length of a, length of b, cosine c. Okay, and again, this is the triangle we're looking at. This is a, b, and a minus b. So if we expand this side, we're just going to square ai minus bi. So we have ai squared minus 2ab plus bi squared, and then equals the same thing on the right side. And then let's expand this again so we can rearrange the sums, right? So we have the sum of ai squared plus the sum of bi squared minus 2 times the sum of ai bi, right? And then that equals, let's see if I can, that all equals what we had up here. ai squared plus bi squared minus 2a b cosine c. So now we can cancel, right? Cancel these, and then we can divide by 2 on both sides. So we cancel the 2 there and the 2 there, and what are we left with? We're left with the sum of ai bi equals the length of a, length of b, cosine of the angle between them. And what's this? This is the dot product. That's how you write the dot product algebraically. And the right-hand side is our cosine. So we can see that indeed, if you add together all the components, you end up with the length of a times the length of b cosine c. That's great. So there you go. That shows why they are, in fact, the same, even though, again, I don't think it's the right way to think about it in terms of the projection, because that implies that we're ending up with a vector in a certain direction, which isn't true. But you can still get the same value in the same way.
Okay, that is it for the dot product. So next up is the determinant, and we will look at how the dot product is related to the determinant and how the determinant gives you the area of the space between two vectors, and then we'll move on to the cross product and how the cross product is used in finding three-dimensional determinants, then the equation of plane and the projective plane. So please come back. Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.